Hello, everyone. We're very pleased today to have Pedro Ochoa from University of California, Irvine. One tends to try to keep introductions brief. I don't know if I'll succeed in that. So Pedro was a PhD student here, and you maybe remember him from his time working in Harvey Newman's group. I worked with him as a postdoc, and he went from here to Berkeley Lab as a Chamberlain Fellow. And then after a brief stint in Chile, he, as faculty at PUC in Chile, he went to UC Irvine, where he's been since 2018. He's one of the, it's very rare in particle physics to have someone with as broad an experimental scope. He is going to tell us about reactor neutrinos, but he's had extensive and continues to have extensive contact with long baseline neutrino experiments, as well as LHC physics, which is almost entirely unheard of for neutrino physicists. He's had significant roles in Atlas. And all of this activity you might expect has been recognized over the years. He's received an award from the Office of the President of Mexico for academic excellence for young scientific researchers. He was recognized very recently from the Chinese Academy of Sciences for US-China partnerships in science. And some of the work he's going to talk about here, particularly the Diabet work, was recognized by the Breakthrough Prize in 2016. That's for the Diabet work, where he's currently the physics coordinator of all of the science that happens at Diabet, and also all of the reactor anti-neutrino science that happens in Juno. I think we'll hear about that today as well. And I mentioned how broad this program is. While we'll hear about anti-neutrinos from reactors today, long baseline experiments are very big in oscillations right now. And he's heavily involved in the DUNE project, which you probably heard about. It's a multi-billion-dollar international project, and he's one of the coordinators in particular of the group that's going to see the first neutrinos in DUNE from a prototype experiment. The DUNE experiment hasn't seen any neutrinos yet, hasn't been built, but there's a prototype that we'll see those soon, and he's overseeing the analysis of that. I could go on, but I should stop here and let him take over. And so, Pedro, why don't you take it away?
Sounds great. Thank you so much. And it's really, honestly, a pleasure to be here. I attended many of these colloquia when I was a student here, working under the supervision of Professor Harvey Newman here. I remember I would sit somewhere over there every time. So today, as Ryan says, I'm going to be telling you about nuclear reactors and how we can use them to understand our world generally through the eyes of neutrinos, if you will. And this here is a photo of the Diabet experiment, which I will be covering in some detail today. So let me just start with a very brief introduction for those of you who are not particle physicists. So we have this thing called the Standard Model. It's our best theory so far of particles, the fundamental constituents of matter, and their interactions. And neutrinos are in this Standard Model. They're included there as particles that have no mass, that come in three varieties: electron neutrino, muon neutrino, tau neutrino. So each one of these neutrinos associated to a corresponding lepton, and then that interact only via the weak force. That is, they have no color charge, they have no electric charge. And in case you're wondering why these neutrinos bear the names of the leptons above them, this is simply because these are what we call flavor states or flavor eigenstates. And so whenever these neutrinos are produced or absorbed, this happens in conjunction or in association with the corresponding lepton. So for example, whenever you have an electron neutrino interacting in your detector, if this interaction is done via charge current interaction, then you will get the electron. And this is how we can identify the flavor of neutrino that we have in our detectors. This story, as far as we know so far, is still accurate, except for the very first statement here. Now we know the neutrinos are not massless, but as best as we can tell, we do know that they interact only via the weak force, also, of course, gravitationally, very, very, very weakly there, which so weakly that we don't even mention that. And it's because of this fact, because of the fact that they only interact via the weak force, that they are so ghostly or elusive. So if I were to shoot a neutrino through the Earth, there's a 99.99999% probability that the neutrino will come out on the other side of the planet. And if we shot a lot of neutrinos through the Earth, then maybe one, maybe two will interact somewhere in the Earth, but most of them will just go through. And this is important to remember because for neutrino physics, this is what we do. We expose big, large detectors to big fluxes of neutrinos, and what we do is a sampling of those big fluxes of neutrinos. Okay, so I think if we want to fully understand our universe, we need to understand neutrinos. And there's at least 3 reasons why this is here. The first one is that they're very valuable messengers. They give us information that's complementary to what we can get, for example, with photons, with light. There's some advantages to neutrinos. They travel directly from their point of creation to our detector. This is also what makes them challenging to detect, as I just mentioned. But again, that means that they're complementary to what we could get through other eyes. Also, they're extremely abundant. They're the second most abundant particle in the universe. That means that they do influence the, for example, large structure formation in the universe. It could be, as we will briefly talk about, that they have, that they can lead us to understand why there's this matter-antimatter asymmetry in the universe. And finally, they behave in a way that currently stands beyond the standard model. And this is great because the standard model is successful, perhaps too much. So what we want is to make an experiment where we see the standard model breaking, and that way we can get a window into beyond the standard model physics. We can get an idea, a better idea of how to extend the standard model. And neutrinos provide us with just that. So the reason this neutrinos provide us with just that is because they oscillate. I'm sure everybody here knows that, but let me just remind you what this means, especially for any students or anybody here who may not be so familiar with neutrino oscillations. I like this cartoon. I've been using it since my days as a PhD student here, which illustrates, I think, pretty clearly what's happening. So if you start with a beam of neutrinos, let's call these cars muon neutrinos, and you let them propagate, then you sample the composition of the beam after a certain distance, then you will find that a fraction of them have changed. In this case, the vans would be tau neutrinos. And then if perhaps you sample it a little bit later, you will perhaps see the third type of neutrino appearing here. This would be the buses, which we represent electron neutrinos, for example. And then if you do this again, you would see that eventually you recover the initial configuration, and this repeats and repeats, hence the name neutrino oscillation. Why does this happen? It's quantum mechanics in its maximum splendor, quantum mechanics that can be seen over macroscopic distances of kilometers or hundreds of kilometers, even thousands of kilometers. So what's happening here is that the neutrinos, the states in which they are created or absorbed, namely electron, muon, and tau neutrinos, the ones that we briefly alluded to in the beginning, they are not states with definite mass. Rather, they are mixtures of these states that have definite mass. We call them mass eigenstates. We label these M1, M2, and M3 for their masses, or nu1, nu2, and nu3 when referring to those states. And so the mixing that happens here is parameterized by a matrix. It's called the PMNS matrix. I'm not going to show you the matrix because I think it's not that enlightening. There's one thing that I do want you to remember, which is that this matrix is parameterized in terms of 3 mixing angles, basically because this is a rotation in 3-dimensional space, and 1 CP violating phase delta. And so what we want to do is figure out what the values of these parameters are. In particular, if delta is not 0, then this means we have CP violation. That would be extremely interesting. I'll come back to this in a second. And with this framework, with this mixing framework, and some basic assumptions, namely the fact that neutrinos propagate as plane waves, then you can take this framework and we can predict what's the probability that if I start with, let's say, an electron antineutrino is going to continue to be an electron antineutrino after traveling for a distance L if that neutrino or antineutrino has energy E. This is a simplified version of what the actual oscillation probability for electron antineutrinos looks like. We call this a disappearance probability because we're looking at the probability that, again, the antineutrino will change into something else. And there is one thing, however, that it's useful to remember. So these mixing angles, they always give us information about the amplitude of the effect, even though, again, I insist the actual full expression is much longer than what I just showed you here. I will show you a little bit later. And then the differences in the squares of the masses, these delta m squares, give us information about the frequency. So give us information about how often this process repeats itself in this L/V space, basically. Okay. So one more thing I should say, if the neutrinos, if these mass eigenstates don't have different masses, the oscillation does not happen. And that is why the discovery that neutrinos do oscillate led us to the discovery that neutrinos, after all, do have a mass, despite the fact that the initial architects of the Standard Model postulated otherwise. Now, this discovery, that neutrinos do oscillate, that they do have a mass, basically opened up a whole new field of research. It also changed the way we look at neutrinos. It changed their role in our universe. And it raised all of these questions that don't yet have an answer. Some of these do, some of these don't. And this is why people like Ryan, myself, and others here are so busy trying to answer all of these questions. So we talked about the fact that neutrinos mix eigenstates of mass, mix with eigenstates of flavor. And so a natural question is what are the values of those mixing parameters? And it's important to pin those down as precisely as possible because they can serve as constraints for models. Also, what are the masses of the neutrinos? They're massive, okay, so what are they? And with oscillation measurements, we can measure the differences in the squares of these masses, but we cannot measure the absolute mass. So this is still a big open question. We have some constraints in cosmology, and also from some direct experiments, but this is still pretty much an open question. How are these masses ordered? So the names, nu1, nu2, nu3, they're completely arbitrary. We could have called them nu Feynman, nu Millikan, nu Lorentz, right? Just to name three famous people from around here. And there's no reason why nu1 should be lighter than nu3. And so we do know, however, that nu2, whose mass is m2, is heavier than m1. We know this from data from the sun, from solar neutrinos, but we don't know if m3 is bigger or smaller than the other two. And we call these two arrangements the normal and the inverted orderings. It's a big question. It has implications for other experiments in neutrino physics. For example, the search for neutrinoless double beta decay, but also in cosmology and many other areas of physics and astrophysics. We don't know if there's more than these three states. It could be that there are neutrinos heavier than half the mass of the Z, for example. It could be that there are sterile neutrinos as well. We'll briefly talk about that. And we don't know, finally, if neutrinos obey or not this CP symmetry, which means, let me try to put it as simply as I can, means that neutrinos and antineutrinos oscillate differently, different between matter and antimatter. And this could give us some hints as to why we have such a difference in the composition of our universe. So how do we address these questions? There's many ways. And today I want to talk to you about one specific one. So one of the best ways is to just create these neutrinos in the lab and study them there. Why? Because it's a controlled environment. There's nothing like you just being able to tune your, for example, neutrino beam. Let me increase the intensity, let me decrease the intensity. That way I can better understand what's happening. It's not so easy to do that with reactors, as you will see. But still, sometimes reactors turn off. You know how the reactor is operating. I will tell you about this. And so there's an advantage there. And also, typically, we can get higher intensity than we can get with natural sources this way. And so the two most common ways of doing neutrinos artificially, of producing neutrinos artificially, is one, using an accelerator, two, using a nuclear reactor. And I'm going to focus today on nuclear reactors because you already have a leading, world-leading program here on accelerator neutrinos. I actually work very closely with some of my colleagues here. I work in the Dune experiment, as Ryan mentioned. We're actually having a lot of fun figuring out how to build a liquid argon TPC that can withstand the extremely high intensity environment of the Dune near detector. And we're making some really nice progress there. But since you already have a group here that's really doing great work in this area, I thought I would focus mostly on reactor neutrinos for today. And so here's the plan for the rest of this talk. I'm gonna give you some basic principles about nuclear reactors and neutrinos. This is gonna be helpful, hopefully, for the rest of the talk. Then I'm gonna look at some recent results. I'm gonna spend a good amount of time here talking about everything that we have learned in the last decade or so. Why? Because we have all this rich data and I just can't resist talking about it. Then we will look at what comes after, and I'm gonna focus about one big, massive experiment that's a next generation experiment. It's called Juno. And then I will finish with a little amuse-bouche of a new approach for detecting neutrinos that has tantalizing applications in reactor neutrino physics, but also beyond. Okay, so let me start with some basic principles about neutrinos and nuclear reactors. And for those of you who are wondering why nuclear reactors, well, it turns out they're fantastic neutrino sources. Why? In case you wonder, let me explain very briefly. What happens is that in a nuclear reactor, you have these heavy elements, for example, uranium-235. And these elements are rich in neutrons. And so when you break them into pieces, you end up with, let's say, one half, another half, that have an excess of neutrons compared to protons, compared to what you need them to be in order to be stable. And so there's going to be a lot of these basically beta decay reactions that are going to happen, and it's going to give you mostly, actually, just to first, second, third approximation, just electron antineutrinos. So a nuclear reactor is a fantastic source of electron antineutrinos. It's the most intense man-made source of electron antineutrinos. You get on the order of 10 to the 20 electron antineutrinos every second for a gigawatt thermal power reactor, which is gigawatt thermal. Just so you get an idea, we're talking about a pretty big commercial nuclear reactor. They're also widely available, nuclear reactors. Not every country has them, but still they're pretty available throughout the world. They're cost effective. Typically, researchers don't have to pay for the cost of operating a nuclear reactor. And as I already said, they're extremely intense. So yeah, I have here one piece of trivia. In 1 minute, you get from a nuclear reactor more neutrinos than in some of the beams that we use for accelerator neutrino experiments. Now, something that's going to be useful to remember for the rest of this talk, there's basically two main categories of nuclear reactors. There's LEU, or low enriched uranium reactors. These are the big, massive nuclear reactors, big commercial nuclear reactors. We're talking about gigawatts of thermal power or more. And the other important thing to remember about these reactors is that the neutrinos that you get out of them, they originate from the fission of 4 isotopes, dominantly uranium-235, but also plutonium-239, as well as plutonium-241 and uranium-238. And so as you burn your fuel, the number of neutrinos coming from uranium-235 decreases, the number of neutrinos coming from plutonium-239 increases. I'll remind you of this when we come back to it a little bit later. There's also highly enriched uranium reactors. These tend to be much smaller reactors with powers on the order of megawatts, tens of megawatts. And these typically are used, again, for mostly research, the production of certain isotopes for medical applications or for different reasons like that. For the purposes of neutrino research, what this means is that if you need to put a detector kilometers away, you're going to want to use mostly these types of reactors because you need the power. But if you want to do a short baseline neutrino experiment, you're going to tend to be closer to these. They're also more compact, which has an advantage. Okay, so how do we detect reactor antineutrinos? We use the inverse beta decay as the primary channel. So in this reaction, we have the electron antineutrino interacting with the proton. You get a positron and a neutron. And the important thing to remember here is that you get two products that you can see. So in these detectors, typically we use scintillator. You're going to hear the word scintillator a lot. The energy, actually, as you can already see here, we're talking about MEVs. For those of you who are used to accelerator experiments, either with neutrinos or with LHC, you're used to talking about GeVs or even higher. And so you're used to mapping out the beautiful interaction, seeing the muon, it went here, seeing the electron went here, then it showered. You see all these beautiful interactions. In these kinds of detectors, our positron here, it just travels for centimeters. We cannot see it. All we see is a flash of light. The neutron comes afterwards, and if you put something in your detector that likes to eat up neutrons, that has a high capture cross-section, to say it better, then it will be excited, and then when it de-excites, it emits a characteristic gamma signal. And this is really the handle that you have for detecting these types of events. The coincidence between the positron and the neutron, the two flashes in succession, is what allows you to identify these events as a primary handle. What else? Here, since the neutron is pretty heavy, most of the energy is carried away by the positron, and so that means that if you measure the energy of the positron, you have a very good idea of the energy of the neutrino. And one more thing, so the spectra that I'll be showing you look like this because it's basically the combination of the flux of neutrinos coming out of a reactor with the IBD cross-section. Now, what can you do with reactor neutrino experiments? You can do all sorts of things, as I will mention, but one of the things you can do is do oscillation measurements. And now here it is, the oscillation probability in its full glory. So this is the full term, ignoring matter effects. And there's a couple of things to notice. One of them is that you have access to 4 out of 6 oscillation parameters here, the 2 independent mass squares, as well as 2 of the 3 mixing angles. There's no dependency here on theta 2,3 or delta CP. This is good. It uses a complementarity with accelerator experiments. And depending on where you put your detector, you have better access to some of these parameters. So for example, if you're interested in measuring theta 1,3, so the red curve here assumes that theta 1,3 is 0. And so this first peak here in blue is what you get if theta 1,3 is not 0. So if you're interested in measuring theta 1,3, you want to go here. You want to go here in this first peak because that means you're pretty close to your reactor. And you're going to be able to see this first peak without, again, having to be very far. You don't need very big detectors. But the disappearance effect is small, so you just have to control your systematics. However, if you want to measure all of these parameters, then you need to go somewhere over here. And that's the case for Juno, as well as the case for Camlet. We will talk about this, but just keep this in mind because this is why the baselines of these experiments that I'm going to talk about are different. So let me show you a couple of results. What have we learned recently when it comes to reactor antineutrino experiments? We have 3 of these that are a kilometer scale baselines. And their main goal was, or still is, to measure the theta 1,3 angle as precisely as possible. In case you're wondering why measure theta 1,3, who cares? Well, we actually do care quite a lot because theta 1,3, we just didn't know what its value was until 2012. It was the last unknown mixing angle in this mixing matrix, PM&S. Also, you need theta 1,3 to not be 0 if there's going to be a chance for us to see CP violation in the leptonic sector. And that's a biggie for the reasons that I already briefly alluded to. And finally, if theta 1,3 is not 0, then those oscillations give us a pathway for measuring things like the ordering, the neutrino mass ordering. And so really the discovery that theta 1,3 is not 0, a spoiler, it ended up being not 0, as I will show you, is really what opened the door to this program of neutrino physics that is happening, is underway already with experiments like NOVA, TTK, but in the future also Dune, Hyper-K, and Juno. So this is why this particular parameter was important for us to determine whether or not it was 0. So there's 3 reactor neutrino experiments at kilometer scale baselines with this single goal of finding theta 1,3. One in China, Diabei, one in France, Double Show, and one in Korea, Reno. And they follow the principles that I already explained. We need short baselines, kilometers, so the detectors don't have to be very big. We're talking about tens of tons, hundreds of tons in the case of Diabei's detectors. We're looking for less than 10% oscillation effects. So the key here, we want to measure this angle precisely, is systematics. And something that you see that is common to these three experiments is this near-far comparison. So what you want to do, again, in order to reduce systematics, since we cannot predict so well what comes out of a nuclear reactor in terms of antineutrinos, you want to cancel out those systematics by making a measurement in the near site and then in the far site. And that also allows you to cancel, to first order, any correlated uncertainties in your efficiencies, for example, because it's much easier for you to determine how efficient I am at detecting antineutrinos in one of the detectors here compared to one of the others here, versus what is the absolute efficiency of these detectors. So the strategy is building identical detectors, putting them in near, far locations, and then using ratios or using comparison between near and far in order to cancel systematics. The three experiments use very similar technology. I'm just going to show Day-to-Day. I'm going to focus on Day-to-Day because it's the one I work on, and also because it's the one with the most precise results. And so this is just an illustration of how those detectors work. These are like, and I apologize for my bad pronunciation, matryoshkas for neutrinos. So you know the doll inside the doll inside the doll. This is a cylinder inside a cylinder inside a cylinder. The innermost cylinder is just liquid scintillator with gadolinium, because the gadolinium likes to eat up neutrons, it gets excited, it gets de-excited, emits a characteristic gamma signal that stands apart, very far apart energy-wise from the radioactivity. Then the surrounding layer is just liquid scintillator to allow you to measure the energy of those events occurring near the boundary well. In the biz, we call this minimizing energy leakage. And then there's a third layer of mineral oil that serves as a shield for radioactivity, coming mostly from the TNT's glass as well as from the stainless steel vessel. And then the detectors, they're very sensitive. Remember, we're looking at MEVs of energy. Those of you, again, working with GeVs, you don't have to worry about this, but we have to worry about all this radioactivity, contamination, and everything coming from the rock and all this stuff. So the detectors are put underwater, and the water is instrumented. So these water tanks, these water pools are instrumented so that we can detect muons, and that way we can reduce backgrounds. So here's a selection of pictures, how this looked like. This is the far site where we have 4 detectors. In the near sites, we had 2. Since the far one is farther away, we need more detectors in order to have bigger amount of statistics. So let me show you the results, our latest results. I cannot resist, showing this. I think it's beautiful data. So this is the data that we see in our far hull. If there were no oscillations, then we should be seeing the blue curve. But what we see are the black dots. And you can see that there's a deficit compared to the blue one. This deficit gets bigger as you get closer to the peak of the spectrum. This is no coincidence, of course. The experiment was designed this way. So in other words, the baseline of the experiment was put in the right place. And then this deficit decreases. If I take the ratio of observation to prediction, I get this dip. And if I fit this, assuming that there's 3 neutrinos, that they oscillate according to the assumptions that I showed you in the beginning, the fit is beautiful, as you can see here. And using the information of how many neutrinos were depleted, how many neutrinos we lost along the way, if you will, the disappearance of these electronegative neutrinos, as well as the energy dependence here, in particular where this dip is, we can extract both theta 1,3 as well as one of the differences in the squares of the masses. And we can do this pretty well now. So these experiments, these reactor experiments, are the best in the world at measuring theta 1,3, and they're probably going to continue to be for the long term. Most likely this measurement that I just showed you is going to remain the best one for who knows how long, but a long time. Maybe Dune, maybe Hyper-K will catch up eventually, but at this moment it looks like it will continue. One thing I do want to highlight in both of these curves, both of these plots here, is that our results from reactor experiments, Reno, Day-to-Day, Double Show, not only they agree between each other, but they also agree with other types of experiments, namely accelerator experiments. And this to me is remarkable. You have, for the one hand side, MEV antineutrinos traveling for kilometer baselines, And then on the other hand, we have muon neutrinos or antineutrinos disappearing over hundreds of kilometers, and we get the same result. So this is really a testament to how good the 3 neutrino framework is. This precision is already pretty impressive, especially for delta m squared, 2%. Juno is going to come and make this 0.2%, and I will come back to that in a little bit. Before jumping to Juno, I thought I should tell you a little bit about where we are with comparing what comes out of a nuclear reactor with what we predict should come out of a nuclear reactor in terms of antineutrinos, because there's some interesting lessons there. So let me do a little digression there, because there's also some lessons specific to sterile neutrinos. So in case you're wondering, why do we care how many neutrinos come out of a nuclear reactor? Because you have your near and your far setup, so you cancel out those uncertainties. And I would say, yes, I agree. That's why we have the near and the far setup. But it's still important to do this kind of physics, because if we manage to fine-tune these models, to improve them, then maybe future experiments don't need to have near-far detectors. There's, for example, searches for physics beyond the standard model happening with the 7th coherent elastic neutrino scattering reaction near nuclear reactors. They could certainly benefit from improved predictions. Also, it's important for reactor monitoring, non-proliferation applications, and for tests of nuclear inputs. Basically, it's one of the best ways to test all the information that is in nuclear databases, to predict the antineutrino spectrum with those data and compare with what we measure in our experiments. And so very briefly, I just tell you here a quick summary of how these predictions are done. One way is the bottom-up approach. It's called ab initio or summation method. And what happens here is from the data of fission yields, what's the probability that I will get these 2 pieces when breaking, for example, uranium-235? What are all the possible ways in which these pieces can decay? I can sum up all those branches and make the spectrum. That's one approach. There's another approach, which is you go to a reactor. This happened in ILL in Grenoble, France in the 80s. So this is pretty old data. You have some foils of uranium-235, plutonium-239, plutonium-241, and you expose them to neutrons so that you induce fission. And then you measure the beta spectrum, so the electrons. And then you convert the beta spectra to antineutrino spectrum by fitting with virtual branches. This is called a conversion approach, and the latest implementation of this approach is called the Huber-Mueller method, which you will hear me talk about throughout the next few slides. So in the last decade, experiments like Diabay came and showed that there's some big disagreements, well, big, I mean, significant, but still actually the glass is half full. There's some maybe 6%, 5% disagreement in the rate. So the flux of antineutrinos coming out of a nuclear reactor that we measure from all of these experiments, as I said, is about 5 to 6% lower than what the conversion method predicts. This is called the reactor antineutrino anomaly. And also, we found that the shape agrees largely, but there are some features. In particular, there's a bump. Here we show model over data. That's why it looks like a dip. But normally we plot data over model, so this looks like a bump. And so we call this the 5 MeV bump. And there are other features again, but this is the most noteworthy. And so this one in particular drew a good amount of attention. What could be causing this? Could it be that all of these experiments are making the same mistake, basically a correlated systematic? It's extremely unlikely, because not only the number of experiments is large, but we all use different technologies. Could it be that there's new physics? And you could explain this with oscillations to a sterile neutrino that is pretty massive, so in the order of 1 eV. And what would be happening here is that the oscillation is so fast, no detector so far at least can resolve it, and you just see like a deficit. And so that's one possibility. It's an exciting possibility. Or could it be that we just don't know how to predict as well as we thought what comes out of the nuclear reactor. And so, well, if you have a hypothesis here of a sterile neutrino, you can actually go and test it. You can put a detector at short baseline from a reactor. And if you want to do this again, it's more advantageous to go to an HEU, highly enriched uranium reactor. This has been done. Most of these experiments have now released results. And you can see if you find an oscillation signal. And so far, we've come up empty. So all of these are exclusion contours. This would be the mixing angle. This would be maximal mixing, of course. This goes in the direction of no mixing. And as you can see, we exclude with these experiments that I just showed you in the previous slide, as well as with diabase, double show and Reno, we exclude a pretty big region of parameter space. We do not see good evidence of sterile neutrino mixing. The parameter space allowed by the reactor anti-neutrino anomaly, by the way, I forgot to say, is this space here in gray. So we haven't covered all of it. We haven't excluded all of it, but still it looks like there's nothing there. By the way, there's a claim from one of these experiments, but in my humble opinion, the evidence at this point is not good enough. So what is causing this discrepancy then? And we've made some headway in answering this question. So in experiments like diabase, remember what I mentioned, you burn your uranium-235, you create or breed plutonium-239. And so the number of antineutrinos from uranium is decreasing as you go through your fuel, as you burn up, as you burn your fuel. And so it turns out that the number of antineutrinos that you get per fission of uranium-235 is larger than what you get per fission of 239. And so that means that if you look at the evolution of the rate of the flux as a function again of how many of burn up, then you expect a decrease. And this is what we see. And if we make some assumptions on the numbers, so the number of neutrinos per fission of the two smallest contributors, plutonium-241 and uranium-238, we can actually fit this data and extract how many neutrinos per fission we get for uranium-235 and for plutonium-239. And we can do this in total, and we can do this as a function of energy. In other words, we can extract the spectra for fissions of uranium-235, plutonium-239, and again, we can also look at the total. And let me draw your attention here to this plot first. So the model, the conversion model is this one. The measurement is are the ellipses in green. The y-axis is plutonium, the yield, basically how many neutrinos per fission, weighted by IBD cross-section. And the x-axis is uranium. So you can see that for plutonium, we're in pretty good agreement. But for uranium, there's a tension of almost 8%. So what this is telling us is that indeed, there appears to be a problem with the prediction, but just for uranium. And this, in turn, weakens the sterile neutrino hypothesis, because if this deficit that we see in the number of antineutrinos was due to sterile neutrinos, it should not just be in the uranium-235 channel, it should be everywhere. The spectra, we can compare the measurement with the prediction, and in both cases, we see the bump, the famous 5 MeV bump. So far it looks like the bump is in both uranium-235 and plutonium-239. And so this is a busy plot, but it's a summary. Let me just put it this way. Conversion models tell us we should be here, 1 and 1. This is the prediction for uranium-235, plutonium-231, based on conversion models, specifically the Huber-Mueller model. If you do another conversion model, not surprisingly, it also falls around here. The data, however, tell us we are somewhere here, though, which means for uranium-235, really the yield is smaller than what a conversion model predicts. But for plutonium, we're pretty close to where we should be. And so this means that the sterile neutrino hypothesis is not completely ruled out, of course, but at least in my humble opinion, it is definitely weakened. We have a good hypothesis as to what is happening here. turns out it's just issues with nuclear physics and the prediction. Now let me jump to what lies in the future for this field. I just try to summarize where we are right now. What's coming soon? And I'm going to focus on Juno because it's the big next generation experiment that's going to dominate basically our field for the next few decades. So Juno stands for Geomet Underground Neutrino Observatory. And this one is going to be, instead of just a few kilometers away from the reactor, it's going to be 52.5 to be precise, kilometers away from the reactors. Since we need as many statistics as possible, as much statistics as possible, we need to be as close to as many reactors as possible. And so we are in a region of China where we can be close to 8 nuclear reactors at the same baseline of 52.5 kilometers. The detection technology is quite similar to what I showed you for diabase. You have a target with liquid scintillator, and then you need to have PMTs looking at this target to detect the light emitted by the positron and the neutron, as we already talked about. And then you need to surround it with water, which is a good shield and also allows you to tag cosmic ray muons and all the associated backgrounds. The only difference is that since you're now farther away, the emission of antineutrinos from a reactor is isotropic, then you need a much more massive detector. So this one is 20 kilotons. So it's 20 times bigger than what would be the second largest liquid scintillator detector so far built, which would be Camland, which was 1 kiloton. And it also has another important feature. It has an exquisite, I think it's justified to use that word, energy resolution, 3% at 1 MeV, whereas a detector like diabase had 8.5% at 1 MeV approximately. Why the resolution? I will show you in a second. But first, how? How do you achieve such a high energy resolution in a detector like this? And there's many conditions that you have to satisfy. The most basic, most important perhaps, is that you need to see more light. You need to increase your light level by a factor of 5 compared to a detector like Camland, which saw 250 photoelectrons per MeV. We need to go at least to 1,200 photoelectrons per MeV. How do you do this? The first thing that comes to mind is let's just put more PMTs in there. But since PMTs are circular, you cannot just fill 100% unless you start using very small PMTs or PMTs with a different shape. So this will buy you about a factor of 2 times more light. You still have more to go. So what else do? You need a scintillator that shines more, that is more transparent. So that will get you closer, but still not good enough. You're still out by a factor of 2. You need photomultiplier tubes that are more sensitive than what was used in Camland, at least a factor of 2. And so I'm not going to be able to cover the details here, but I do want to leave you with this message of how Juno is pushing the limits in liquid scintillator detection technology. The best PMTs we have so far, an optimized liquid scintillator recipe, as best as possible, as many PMTs as we can pack with a tolerance of 3 millimeters between them, pushing the limit in this regard. But of course, this is not enough. You need to calibrate your detector really well, and you need to control those systematics after calibration, what we call the non-stochastic term of the energy resolution, to better than 1% so that we can achieve this 3% of energy resolution. And so again, I'm not going to be able to get into the weeds here, but there's many ways that we do this in Juno. One of them is by putting small PMTs in the space between the large ones, as you can see here. And what this gains us is that the small PMTs operate in photon counting mode in the energy region of interest for reactor antineutrinos. So they're a linear reference with which we can calibrate the large ones. They also have other advantages. They give us a little bit more light, which is welcome because of the reasons that I just said. They also allow us to better reconstruct muons. They extend the dynamic range of the detector. They have all these other pluses, but the main thing is their role as calibrators, as calibration handles for the large PMT system. So why now, going to the why question, why do we need such a good energy resolution in Juno? I hope you remember that plot I showed you in the beginning of how the disappearance when you're farther away from the reactors is much bigger compared to what diabase sees, which was only less than 10%. So here the effect is huge, the oscillation effect is very big. And we expect in Juno to, for the first time, see basically the impact of all these parameters simultaneously. There's a slow wave here. I cannot do it very well here with the pointer, but hopefully you get the idea. There's a slow wave there, and then there's a fast wave riding on top of that one. These are the so-called solar and atmospheric oscillations. And it turns out, depending on which is the right mass ordering, the little structure here will be a little bit different. Basically, the difference between the red and the blue. And so in Juno, if we have a good enough energy resolution, we should be able to tell the difference between the red and the blue curves. This is why we need such a good energy resolution. And so if we do have our 3% at 1 MeV energy resolution, which so far it looks like we will, we should be able to measure the mass ordering in about 6 years to about 3 sigma. And this is a completely different approach for measuring this quantity compared to what accelerator experiments do. And this is nice. There's a very nice complementarity here. And any disagreements between the two experiments would be fun, actually. It would be extremely interesting to pursue. Now, as you can imagine, if we manage to measure this spectrum and tell the difference between the blue and the red, we can measure these parameters really well as well. And so Juno will be measuring 3 of these 4 oscillation parameters to some exquisite, sorry to use that word again, but I think it's appropriate in this case, some exquisite precision. Right now, this is the precision that we have. For theta 1,3, diabase dominates. Juno is not going to be able to improve diabase precision. That's why I said before that probably those measurements we have right now for theta 1,3 are going to be it for the near term at least. For at least as far as we can tell for now. But for the other 3 parameters, the improvement in precision will be basically 1 order of magnitude roughly. So this is going to be one of the nicest measurements coming out of Juno. There's plenty of other things that Juno can do. We can detect geoneutrinos. Even though it looks pretty small here, geoneutrinos are in yellow here. It looks pretty small. It's still hundreds, the order of 400 geoneutrinos every year, which is more than the total amount of geoneutrinos that have been detected by all the experiments operating so far for more than a decade. So Juno in 1 year collects more geoneutrino statistics than what we have right now, with the caveat, of course, that we have this humongous background. In this case, the reactor and neutrinos are the background. But still, we can make a pretty good geoneutrino measurement. We can improve on existing measurements by about a factor of 2 in precision. So Juno is also going to be a leading geoneutrino experiment. And I don't have time to cover the other physics topics, but Juno is also going to do some really nice solar neutrino measurements. For supernova neutrinos, it's going to be a thing of beauty, in my humble opinion, because if we are lucky to have a supernova explosion of the order of 10 kiloparsecs or so, we'll have thousands of events in this detector with very nice energy resolution, low threshold. So it would be a unique data set. And also, we are sensitive to the diffuse supernova neutrino backgrounds. So that means we can detect on the scale of a few years, 5 years, maybe 10, depending on what model it is. We can detect all these supernovas from past explosions. And that, again, is a measurement that hasn't been done before, and it would provide some really nice constraints for astrophysicists. We also do geoneutrinos, as I mentioned. We do searches for new physics, and of course, all the physics with reactor and neutrinos that I already mentioned. I just have some photos here to show you the progress. Construction is well underway. So this is how everything begun. We had this sphere that is maybe 1/3 of the way completed. We have this platform that was being raised. This is a photo of what happened once the outer shell, this stainless steel structure was almost completed. There's still a hole here, but it's almost completed. Here's a person for reference. And this is when the sphere in the beginning, in the center, sorry, that is made of acrylic, that's going to contain the 20 kilotons of liquid scintillator. When it was starting to get built, this is how it looks like now, pretty much. I took this photo about 2 months ago, 3 months ago, and now the acrylic sphere is almost to the equator. The PMTs, ton of PMTs, as I said, packed as tightly as we can. And this is the little train that we take to go on the ground. This is how the detector looks like, again, a few months ago. And here's two people looking at the camera. So I'm almost done. I just have like 3 more slides. If it's okay, let me tell you very briefly about a new idea for detecting neutrinos. So everything I've shown you so far, I hope you realize, I'm sure you realized the technology is very similar. We have a medium, liquid scintillator. It's the medium that produces light when a neutrino interacts there. And it's also the medium that we use to propagate that light to surrounding photosensors. This is how neutrino physics at MeV scales pretty much has been done since the dawn of this field. This is how it's been done since the time of Reines and Cowan. Some of us think it's time to come up with a new approach. How about instead of using transparent scintillator, we use opaque scintillator? This sounds absolutely crazy, right? If you were to just put opaque scintillator and fill Juno with that, it would be the worst detector in history, of course. You wouldn't see anything useful there. But the advantage of the opacity is that it allows to keep the light near its creation point. By opaque scintillator, by the way, we mean a scintillator that has long absorption length, but short scattering length. So it's a scintillator where light bounces a lot, but doesn't get so easily absorbed. So we're talking about scintillators that look more to your eye like milk, as opposed to something that looks like this, very dark, like dark beer. So again, why would we do such a crazy thing? The advantage is that you keep the light near the creation point, and that allows you to preserve the topological information of the interaction. And then, of course, again, if you just surround your detector with photomultiplier tubes, it's useless. What you need to do is you need to dig in there and extract the light. And we do this by running an array of fibers in at least one direction. The light captures on the fiber, it's wavelength shifted, travels along the fiber to a sensor, to a photosensor. What this buys you is, for the first time ever, pretty much, topological information at the MeV scale. Right now, we cannot tell the difference in a detector like IAA or like Juno between an electron and a gamma. They just look like flashes of light, as I mentioned before. We can tell where the vertex is to a few centimeters of precision, maybe 10 centimeters even. We can tell the energy pretty well, but we cannot distinguish those two. It's a gamma, it's an electron, who knows? With a detector like this, you could. Let me explain these two pictures. This would be a positron. The positron deposits its energy over centimeters. You cannot see that again. As the light is emitted, it's trapped because of the opacity of the scintillator. So you get a light bulb here at the center. Once the positron has stopped, it annihilates with an electron, and you have two gammas back to back. One gamma goes this way, the other gamma goes this way. As the gammas travel, they lose their energy at these energies primarily via Compton scattering. And so it knocks out an electron, and each one of these knocked out electrons is a light bulb. We call these light bulbs, as I mentioned here. So a positron is a central light bulb with all these other light bulbs detaching from the central one. If this was transparent scintillator, the information is lost. Flash of light. A gamma, however, looks like a succession of these bubbles, rather than, again, the detachment from a central one. And an electron is just a single light bulb. So this is a way to identify or separate on an event-by-event basis these types of interactions, of events, at the MEV level, which again has not been done, at least not to this level. There's an additional advantage, which is that if you no longer care for transparency, it's a lot easier to just load your scintillator with tellurium, for example, or whatever you're using for your, for example, neutrinoless double beta decay experiments. So that's an additional plus. We have some preliminary results from a prototype. We call it mini liquido. We have 56 fibers running in 2 directions. We have a beam of electrons impinging from the bottom. And so that means we use a Mylar sheet so that the electron deposits pretty much all of its energy in the scintillator. So that means we expect the creation of a light bulb here at the bottom. And so if you plot, there's many ways to visualize the data. I only have to pick one plot. This is the way we like to. We think it illustrates best what's happening here. We use a scintillator whose scattering length changes with temperature. If you lower the temperature, it becomes more milky. If you increase the temperature, it becomes more transparent. It's called no wash. That's an ugly name, but that's what we call it. So it's what this NW stands for. And so ignore water here. If you look at lab, as you expect, you get more light closer to where the beam spot is as opposed to when you're farther away. That's what you see here in this red curve. But as you decrease the temperature, if you fill this with no wash, if you decrease the temperature, you increase the scattering, decrease the scattering length. There's more opacity, in other words. And this curve does this, as you can see by comparing the red with the blue. You are now detecting more light on the fibers that are closer to the beam spot, significantly less light in those fibers that are farther away. This is the light bulb. You're seeing a light bulb getting created here. These results are going to be published soon. I'll be happy to discuss more in detail soon, but let me just mention before finishing, we're getting started here. We have a demonstrated fund that is called Cloud. We're going to put it near a nuclear reactor in Show, actually, because it's a great environment to test this new technology. It's a very well understood environment. We have all these positrons from all these IBD events that we can use for discriminating between positrons, IBD, gamma, etc. Sorry, positron, gammas, electrons. So it's a great place to test the performance of a new detector like this. But it has many other applications beyond reactor and neutrinos. For example, it could be used for neutrinoless double beta decay because you have the better signal to background handling performance. And also because you can load, should be a lot easier to load a detector like this compared to what you can do, for example, in Cameron Zen, where you need the transparency. So I'll finish here. Nuclear reactors, excellent neutrino sources, many advantages. A lot of cutting edge neutrino physics have been done with nuclear reactors. They continue to be done. We have measurements of oscillation parameters. We have searches for cell neutrinos, and we also have all these high precision absolute measurements of flux and spectral shape for reactor and neutrinos. And then I think this field is continuing to grow. Now there's this massive next generation experiment called Juno that's going to take the field forward, that's going to answer some of the most pressing questions that we have in neutrino physics with a unique approach, really complementary to what can be done in other experiments. And also it's going to be used for many other things, such as testing exciting, fun ideas like the one that I mentioned to you here at the end. So as always, well, it's not always the case, but we've had some exciting surprises lately, and we think, / hope, this is going to continue to be the case. So thank you so much, and I'll stop here.
Thank you, Pedro. Let's have some questions.
Please.
So I'm not a particle physicist, so I just need to ask real quick, what is, 30 seconds, what's a sterile neutrino of bio?
A sterile neutrino is a neutrino a hypothetical neutrino that would not interact. So the only way we could detect it is because it would modify the oscillation pattern that we see in the 3 active neutrinos. And so that's why we're looking for example, an additional oscillation frequency in our experiments. By the way, it's a good candidate for example, dark matter, because it would interact gravitationally. The sterile neutrino could be pretty heavy, but it would not interact in our detectors. Yeah.
Pedro, I have a quick question. So with cloud, I might have thought that the next step in R&D sort of prototyping program would be just radioactive sources. Why go all the way to a nuclear reactor with this?
I skipped a little bit. So what you're saying is happening, definitely. Starting from this one, from this prototype, which we're not using a radioactive source, but we're using a beam spectrometer, which is better. But there's going to be a larger version of this. We call it mini gamma. And then we're going straight to this one. So there's a couple of stages there that I skipped just for brevity. But indeed, there's a couple prototypes that will happen before this one. This one, we don't yet have a design, even though it's funded. We need to build the prototype, this mini gamma that I was referring to first, get some results there, and then we'll finalize the design of this one.
So I was thinking about liquid was very exciting, but you laid out the Juno plan, which is going to happen very soon, and it will measure especially the neutrino side of things extremely precisely.
Yeah.
So with liquid O, I mean, there is all of the other program that you mentioned, and of course, great resolution is always welcome. But aside from reactor neutrinos, what are the other uses?
Yeah, exactly. So I personally think liquido near a nuclear reactor, its best use is to demonstrate liquido, because again, it's a very well understood environment. It has some advantages. We already have pretty low backgrounds. I don't know if you remember that plot that I showed you from Diabay. Our backgrounds are already smaller than 3%. With liquido, we would bring it to close to 0, except for any irreducible backgrounds. At least all the correlated backgrounds, we would bring them very close to the 0. We would still have the accidental backgrounds. We wouldn't need all this shielding that I mentioned before, all the water around. We can dispose of that pretty much with a liquido light detector near a nuclear reactor. So it does have those advantages. But I agree, and I think its best application is not so much with reactor antineutrinos. One area I'm particularly excited about, and which I briefly alluded to at the end, would be neutrinoless double beta decay, because that's an area where you really need to control your backgrounds really well. And that's something that liquido can do, right? Distinguish gammas from betas. The double beta decay signal is a nice big light bulb, as opposed to all the gamma backgrounds, which are the multiple light bulbs. And also because of what I mentioned about the loading, that it should, R&D is ongoing, that's why I'm careful, it should be easier, much easier, to load a detector like liquido with a bunch of, a lot of isotope. For example, tellurium, I was mentioning tellurium because of Kamlin-Zen, as opposed to a detector where you need transparency. So that's an area I'm particularly excited about, but there's others. You can do some nice solar neutrinos with a detector like liquido. There's these reactions first proposed by Raghavan a long time ago, but it was the 60s. In a detector like liquido, you would have a triple coincidence, and you have the topology information. So you would be able to perhaps do some nice PP solar neutrinos spectroscopy. Accelerated neutrinos also, it's challenging to scale a detector like liquido to the size of the far detector of Dune, but it could be useful for one of the components of a near detector, for example. So there's many areas that we're looking into. Also geoneutrinos, even though it's not in the list, there's a paper we published recently showing that we could, in principle, see geoneutrinos from potassium. This is a holy grail because it's below the IBD threshold. So we would not be using the IBD reaction. The caveat, look at our paper, but the caveat is that you need a monstrous liquido detector to do that, but at least it's a way. So we're looking at different options.
Since the 5 MeV bomb persists, what are the ideas about modifications?
Yeah, that's a very good question. So indeed, that one persists, and we don't know where it's coming from. It could be new physics, although not a sterile neutrino, certainly. It will have to be something perhaps even more exotic. Well, I don't know if it's more exotic, but it would have to be some NSI or something like that. And even those scenarios have been mostly ruled out now. It looks like it's just nuclear physics is the most likely possibility there. And the fun thing or the funny thing about this shape anomaly, I did not allude to this very in detail because of time, but that's why I put this plot here. We see this bump when we compare with conversion models, as well as when we compare with summation models. So it's got to be something common to both. And I'm gonna stop there because I think that's as far as we know. Probably some of the branches that are used for both of these models, some common input to both. So I hope I answer your question. That's where we're at.
But you alluded to this reactor anomaly. I think I would put it a little stronger. I think it's sort of dead. Because
I agree. I was being very cautious. It's
there are
weakened.
so many things which
Exactly.
each of them is not really convincing, but
Yes.
together I think they're
There's.
really clear.
I agree.
And it's also really clear what happened
Yeah.
that in Grenoble in that experiment, presumably uranium-235 normalization was not measured correctly.
Yeah. Exactly. I did not have time to mention that, but what Professor Vogel is alluding to is this brown line. These measurements from ILL that I described briefly that were done in the 80s, they were redone recently at the Kurchatov Institute. Not exactly the same. So rather than looking at the beta spectra for uranium-235 and plutonium, they look at the ratio. And it appears that the ratio is off. These results did not explain the shape. There's no bump in these new data, but there is a difference in the normalization. And so the confluence of all these data really suggests, it's a problem in this modeling of uranium-235 coming from those old ILL measurements in the 80s. But I'm trying to be super cautious here. You never know, right? But yeah, I think also it's almost dead.
All right, one last question, and then we should take for time. Will Juno have any angular resolution?
Yeah, of course, it depends on energy, as it normally does. It's a few degrees, which is surprising for a liquid scintillator detector, but we can do well thanks to all the PMTs and the fact that the small PMTs give us good timing, etc. So because of different reasons, we do have some angular resolution, but it's not, of course, as good as an experiment like Pingu or well, not Pingu anymore, but an Ice Cube or even in Dune or in other experiments. So we can do atmospheric neutrino oscillations in Juno. We can get like 1 or 2 sigmas that can add up to our 3 sigmas that we get with the reactor antineutrino measurements. And again, the main limitation is the angular resolution.
So of course you can detect supernovas.
Yes, indeed, and not just for a burst, but as I mentioned, also the diffuse supernova neutrino background. And that's something I'm particularly very excited about.
All right, I think we should pause there and thank you again.